So if you can have out this sheet you picked up on the way in, I'm not going to read the top paragraph. My hope is by doing the reading guide, we understand what I was trying to get at with these graphs. Now, one of the things that you want to be able to do, so what I would have listed as a specific goal of the day, is how can we determine if the order of the reaction is 0, first, or second order? One of the ways is by looking at the graphs. As I explained to a few of you, the lab that we're going to be doing in January does just this. That we're going to be taking a purple solution. It's called a crystal violet solution. We're reacting with sodium hydroxide. And over time, it becomes less and less purple because it's reacting. So it's changing in color. We can measure using a spectrophotometer then what is the new concentration after 1 minute, after 2 minutes, after 20 minutes. That's how long we take to do it. And then we can graph it. And you notice on this first set of 3 graphs, I have concentration versus time, natural log versus time, and 1 over concentration versus time. Only this one is linear. In fact, notice they say the K value, the rate law constant, it might be hard to see on mine, sorry, equals the negative slope. So in other words, if this slope value that you could solve for, take the opposite, and that would be the rate law constant. That's another way we could solve for K. In the second set of 3, notice it's the natural log versus time graph that's giving us a linear graph. And once again, they relate that to the K value. In the third set of 3, it's the 1 over concentration. I did these in numerical order, where the first row of 3 would be a 0 order reaction. So if it's concentration versus time that gives you a linear graph, that's a 0 order reaction. A first order reaction would be the natural log of the concentration versus time. And then this bottom one, because again this is in numerical order, would be the second order reaction. So one of the things that you should be able to do is look at a graph and determine which one is linear. If we go back at the equation sheet here, they put the first order reaction one first, they put the second one second. So do you have to memorize natural log as first order? Not necessarily, because this is the sheet that you're given. Why they don't give you 0 order, I'm not sure, but just get rid of the natural log parts. Again, these equations could be used to solve for K as well, because if I know my initial concentration, that's concentration at time 0, and I know my concentration at whatever other time, let's call it 10 minutes, I could plug that in, I could have my 10 here, and maybe it's worthwhile knowing how to press the LN button on your calculator and then typing a number to get that. Quite frankly, when we do our graphic analysis in January, we're going to set up our Google Sheet where if we type in the absorbance, our y equals mx plus b equation will tell us immediately the concentration. And then we're going to program in the next column where it'll just take the natural log of that value. And then we're going to program in the next column where it's just going to take 1 over that. So by doing a little bit of computer manipulation with Google Sheets, we can type in an absorbance. It's going to give us all the data we need, and then we're going to make graphs with that as well. But I wanted to point out these equations as well. Lastly, half-life. This is the half-life for the first order reaction. They typically don't ask you anything about the other ones, but this is another way to solve for K. You saw a half-life question in the reading guide where, you know, half the time, half-life is just how much time does it take for half of the concentration to go away. If I start with 1 molar and now it's down to 0.5, how long did that take? If you know how long that takes, you can solve for your K value using this equation right here. So I wanted to first off show you the graphs, show you how that relates to these equations, because I would hope, especially now that we're getting more and more, I mean, look right above equilibrium, there's a lot of math here. But as we get into more work here, being familiar with these equations helps you out on our test, even sometimes if we don't use the equations. Again, first order is the first one, so natural log should be a linear graph. Okay, On the backside, so if you flip to the backside, I'm trying to do the opposite. I am trying to give you lab data instead. And the first 4 questions are all dealing with, if you have one reactant, how can I determine the order of the reaction for that one reactant? And then when I get into questions 5 and 6, there's 2 reactants, a little bit different. Notice in number 4, instead of giving you a concentration, I'm giving you pressure. Pressure and concentration can kind of be treated the same. I actually want to do number 4 with you right now. What happened in number 4 for this reaction is every 10 minutes, pressure was measured. And what I noticed for this first column is after the first 10 minutes, my pressure goes down by 1.5. Right? And the second 10 minutes, my pressure goes down by 0.75. Then it goes down by 0.37. When we look at which graph is linear to determine order of reaction, because that's a change in concentration over time, we want to look at the change of this per time as well. So again, what I noticed in this first one is that this changed by 1.5. This changed by 0.75, 0.37. My change, my change is not linear for this. That tells me that this cannot be a zero order reaction, because whether it's concentration or if it's pressure, if the change is the same each time, that indicates that it's going to be linear on a graph. Now know which graph is which for linear. If I look at the natural log of these, 1.1 minus 0.4, that's roughly 0.7. 0.4 minus 0.29, that's roughly 0.7. Negative 0.29 minus that, roughly 0.7. Notice how this change is the same. This would give you a linear graph. And if the natural log gives you a linear graph, it's got to be first order. I wouldn't even look at the 1 over concentration, because that won't give you linear results. Now, I could see this problem number 4 being on your test in a multiple choice format. Because do you need a calculator to subtract 2 numbers? Hope not. Questions 1, 2, and 3 I put on here, I only gave you concentration. That we could not give you on the multiple choice portion. Because, Grant, do you know the natural log of 0.02 in your head? No. You can't just use a piece of paper to figure that out? How do you even do that? I asked Ms. Schrader once, what is natural log? She's like, well, you know, like you got 10 to the x, and then you got the logarithm. Well, it's like that, but it's for e instead. I'm like, well, what's e? Well, it's just this number that they use to figure out some point that makes math work. I mean, pi just makes circle math work, right? So, really, what is it? Who knows? You'd have to type it into your calculator, though. If you were to do questions 1, 2, and 3 on here, I would look and see, does the concentration, is that linear decrease over time? If not, I would take the natural log of each of these numbers and then look and see, is that linear over time? If not, I would do 1 over concentration each time and see if that decrease was linear. Now, I'm not going to go over these 3 problems with you right now. However, if you needed more practice, that's what you would do on these 3. Is you would simply look at first concentration. If that's linear, boom, you're done. It's zero order reaction. But if it's not, then you have to get out your calculator and you got to start figuring out the natural log of each of those values and then look at the change over time. So questions 1 through 4 on that back side are all dealing with one reactant. 5 and 6 are dealing with 2 reactants. So I'd like to go over number 5 with you to kind of wrap up today. if you have two different reactants, and you saw a problem like this on the reading guide, we need to give you multiple trials, at minimum 3. What we want to do is see how each individual reactant affects the rate of the reaction. So in my trials 1 and 2 on this question number 5, my H2 concentration remains constant at 0.3. However, when I go from trial 2 to trial 1, I double my NO concentration from 0.1 to 0.2. So what I would do then is see what happens to my rate from trial 2 to trial 1. When I double my NO, that changes by a factor of 4. So 2 to the second power. That means it's second order in terms of NO. Now, I could have tripled my NO, and that means then this would have went up by a factor of 9. I could have, you can change the concentration in whatever way you want. Remember, if it's second order, it's to the second power. Now, if I look at trials 2 and 3, the NO concentration is the same. And again, I gave you a little bit weird data here, where from trial 3 to trial 2, it increases by 1.5, 2 to 0.3. This also increases by 1.5. So whatever I do to the concentration of a reactant, if it has the exact same effect on the rate of a reaction, that's first order. Again, whatever I do to the concentration of a reactant, if it does that squared, it's second order. If it doesn't do anything to the rate, it's 0 order. If I were to write the rate law for this, it would be rate equals K times the concentration of NO to the second power times the concentration of H2 to the first power. Now, question 5 isn't asking me to do that, but I wanted to give you that information. Question 5 says, what's the order for each reactant and the total order of the reaction? The total order of the reaction would be adding up these two values to say that it's third order overall. It's second order in respect to NO. It's first order in respect to H2. It's third order overall. Number 6 does the exact same thing, except for it gives you pressure instead of concentration, because again, if we're dealing with a gas, and eventually you have to realize we're getting to the point where we're learning enough material where we can start to combine multiple topics, especially if it was a final exam come January. We can have a gas law question that all of a sudden drops in this data and asks you for the order of a reaction. So remember, if I change the concentration of one thing and it has no effect on the rate, it's 0 order. If it's the exact same effect, first order. If it takes that squared, second order. So really, that's our goal today, is to go over how to identify the order of a reaction. And remember, there was a question in the reading guide that asked you to solve for K. If you have this data, plug in any trial, and you can solve for then the K value.